Hello, everyone. Today we're going to pick up where we left off last time, talking about kinetics. Where we left off, we were talking about how to solve for K and looking at zero order, first order, second order reactions, and how finding out what those are gives us the coefficients that we put with the respective concentrations of the reactants. In this case, if it's a 2, it's a second order. If it's a 0, it's a 0 order. And if it was a 1, or if there was nothing there, it would be a first order. And we left off with a few problems where we looked at the relationship between the concentrations changing or remaining constant over different measurements, and how those changes or lack thereof were related to the change in the rate. Okay, and so I know that in the syllabus it says that we're going to cover kinetics just in this week, but I wanted to kind of slow down the rate at which we go through this topic, because I don't want to proceed too quickly and not cover this with the depth that I'd like to, because again, this is an important topic for Chem 103. So we will pick up talking more about first, second, and zero order reactions in this lecture, and then next week we'll wrap up kinetics. Okay, so let's share the screen and begin. Okay. So what we're going to be talking about today is integrated rate laws. And just to give you a quick review of what we discussed last time, we talked about kinetics being the rate at which reactions take place, and that a rate is a measure of how properties vary over time. The reaction rate is the change in the amount of a reactant or product in a given amount of time. And that the rate law is this: the rate equals the rate constant times the concentration of the reactants to some kind of power, M, N, P, etc. Okay, and that this power is not the coefficient in the formula, but rather whether or not these reactants are first, second, or zero order reactions, right? And again, we talked about how we can figure out what order those are by looking at the relationship between the change in concentrations over time and the change in the rates over time, right? So let's say if concentration of one reactant doubles and the concentration of the other reactant stays the same, remains constant, and the overall rate doubles, then that would be a one-to-one interaction between the concentration of the reactant and the rate, and therefore it would be a first order. But let's say the concentration doubled and the rate quadrupled. Well, then that would be a second order reaction. And so then the coefficient M, N, etc., that would be 2. Now, if the concentration doubled or tripled or quadrupled and the rate stayed the same, then we know that that reactant has no effect on the rate, and therefore it would be a 0 exponent. It would be a 0 order reaction. Okay. Rate laws allow us to relate the rate of something and the concentration of something. In this case, that something is reactants, right? So we were looking at how the concentration change affects the rate change. What integrated rate law allows us to do is to set up an equation to relate the concentration of a reactant to time, okay? Concentration of reactant to time. So for instance, if we wanted to know how much of a reactant or product is still around after a given period of time, we could use integrated rate law. So if we wanted to look at radioactivity, for instance, to see how long it took for some radioisotope to break down to something that was stable and no longer dangerous to us, we could use integrated rate law. Or, if we're looking at C14 carbon dating and want to know how long it takes for C14 to break down to C12, we could use integrated rate law. We can also use this to see how much time is required for a reaction to proceed to a certain extent. For instance, with chlorofluorocarbons or CFCs, they take quite a while to react. And so these are pollutants in the environment, in the atmosphere. They're also can be found in your barbecue grill. And so if we wanted to see how long it took for them to essentially not be pollutants in the atmosphere, we could use integrated rate law and see how long it would take to clean up the air from CFCs. Okay. Now, let's just dive right in. Integrated rate laws. What this is we're going to say, let's simplify this reaction of A plus B yields C plus D. And we're just going to say A, because we're looking at that particular reactant, goes forth into the products. If we're looking at a first order integrated rate law, we're going to use this simplified reaction, right? This A yields products as a first order. And we're going to say that that rate is directly proportional to the concentration of A. So rate equals the constant times the concentration of A, right? And it's to the one, or we don't have to write anything here because anything to the one is just itself. And since we already know previously that the rate equals the negative change in the concentration over the change in time, right? We learned that from last lecture. We can say that the negative change in concentration over the change in time is equal to K times the concentration of A. Okay. Now, we haven't really integrated anything yet. We're just setting this up for the integration. And I'm not going to go into integrations too heavily. It's calculus, and it's not really in the scope of this class, but I think a lot of you have already taken calculus or are taking it. And so, if you really want to know the ins and outs, you can brush up on it there. We'll just make some assumptions here. All right. Okay. So the reaction above, let's say it's first order for A. Okay. And B is zero order, so it has no effect on the rate law. We could write it again as this negative change in concentration over change in time equals K times concentration of A. And we could essentially just rearrange things a little bit to get this, right? We want to get the change in T over here with K, and we want to get the concentration of A over here with the change in concentration. Okay, so if we just use basic algebra, we can rearrange that top equation. And from there, we can integrate both sides of this equation and get the natural log of concentration A subscript time over concentration A0 equals a negative KT. Okay, that is our integration. Okay, so we take that, we get this integrated equation, and that becomes our integrated rate law. And again, what this allows us to do is look at the relationship between concentration of our reactants and time. Okay, because what we have here is the concentration of reactant A in terms of time. So that's the concentration of A at any given time. K is, again, our rate constant, and A subscript 0 is the initial concentration of A, okay? So we can compare the initial concentration that we start off with to the concentration as it's decaying or as it's proceeding to react to products. We can look at that at any time, any point in time, and see what it is relative to its rate constant and its starting initial concentration. Now, taking that integrated rate law, we can, again, use certain procedures to manipulate this equation. If we wanted to get rid of the natural log, we could take this first equation. Let's start writing a little bit here. We could take this first equation here and go down to this. And remember, that's what happened to my getting rid of the natural log makes it e to the negative of our kt. Or we could say that this becomes this, where the natural log of AT over A0 is the same as saying the natural log of AT minus the natural log of A0. And then finally, if we wanted to just get the natural log of AT by itself, we could add the natural log of A0 to both sides and get this equation here, right? And this is the one right here that we're going to focus on later on in the lecture for this kind of format of this integrated rate law for first order, second order, and zero order reactions. Okay. Let's try it, shall we? That's weird. This actually, I don't know why that is hanging down like that, but this should be right here. Let's practice it out. The rate constant for a first order decomposition of cyclobutane at 500 C is 9.2 times 10 to the negative third per second. Okay. Now, here's the formula here. And they're saying that how long will it take for 80% of a sample of cyclobutane to decompose? Now, in order to do this, you have to figure out what you're solving for. Well, we're going to be solving for T because it's saying how long, okay? And that's the giveaway. How long? So we're solving for T. Will it take for 80% of a sample to decompose? So we have, what do we have? We have this, which is K, right? That is our rate constant. And that's about it, right? We don't know the concentration, but we don't really need to, okay? Because they're saying 80% of the sample. How long will it take for 80% to break down? And remember, this right here, I gotta move something out of the way. This right here is just a ratio, right? Essentially, it's just the ratio of that concentration at a particular time over the concentration initially. Okay, so you're dividing those two. So it really doesn't matter if they're asking for a percentage. We could put any numbers in there, right? And 80% of it, or 20%, which would be right, what's left over, that is going to be the same if you can arbitrarily put numbers in there, is what I'm saying, and it won't change the overall answer. All right. So pause here, see if you can work on this, see if you can figure out what to do for A. And if you know that, then you should be able to solve it. Okay, so to start this problem, I wrote out the integrated rate law, and I switched the A0 and AT. I flipped them, and that made this positive, okay? Because remember, the natural log of AT over A0 is equal to negative KT. But if you do the reciprocal of that, then ouch, reciprocal of the sign. So now it becomes positive. And we're solving for t, right? They want to know how long it's going to take. So to get t by itself, we can use some algebra, and we get this format here. Okay, and so now what we have to do is plug in our values. Again, as I said, we don't know the concentrations, but we know the relationship. We know the relationship is, it said, how long will it take for 80% of the sample to decompose? And so if we're looking at the initial, what we're saying is what's left at this particular time. Well, if 80%'s gone, then there's 20% left. So there's going to be 20% of this initial concentration, right? So that you could put in any number, right? You could put in, if your initial concentration was 1, it would be 1 over 1 times 20%, right? And whatever you want, but essentially 20% is a factor of 5. Okay, so it doesn't matter what value we put in here, it's essentially going to be 5. So let's just for simplicity's sake, let's just put 1 here and 0.2. Okay, because 0.2 is 20% of 1, right? And then the K was 9.2 times 10 to the negative third per second. Okay, and so if we do the math on that, we end up with T equaling 1.609 times 1 over 9.2 times 10 to the negative third per second per second. And then that equals 1.7 times 10 to the 2 seconds. Okay, that's basic usage of integrated rate laws right there. All right. Now, okay, so what we've said is that integrating this equation, we get this setup here, or we get this setup down here. And this is what we used to answer the last problem, solving for time. But this is one that we're going to focus on more heavily because it is similar in its transform to another equation that I'll get into in a moment right here. Okay, notice that the integrated rate law kind of is similar to the equation for a line, right? For this slope, we have y equals mx plus b, right? So something equals something plus something. Here we have something equals something plus something. And believe it or not, with a first order reaction, if you were to plot the natural log of a concentration of a reactant as a function of time, so as it is changing, how that concentration is changing over time, you should get a straight line right here. Okay, as it's, you know, the concentration, the natural log is on the y, time is on the x, and what we have is the slope of negative k, or the slope is equal to negative k, and the y-intercept up here is the natural log of the initial concentration. Okay, hopefully that makes sense. Essentially, we are superimposing these two equations right here as we plot a first order reaction. Okay, and you should get a straight line. If you don't, something went wrong. And so here, let's think about an example. Let's say we have methyl isonitrile, and right here, and it converts into acetonitrile right here. And it's a first order reaction. If we just plot the change in pressure of our methyl isonitrile, you see that it goes down over time, and it's slightly curved. Okay, but then if you take the if you take the natural log of that pressure right here, it transforms it into a straight line. Here, there's no natural log, it's just the raw values. Changing that to natural log gives you a straight line. Okay, and so because it's that straight line, we know that the process is first order and that k is equal to the negative slope. Okay, so if the slope is 5.1 times 10 to the negative fifth, then k is going to be negative. Well, I guess the slope would be a negative 5.1 times 10 to the negative fifth. So then the k would be positive, yeah, because it's a negative of that. So it'd be 5.1 times 10 to the negative fifth per second. Okay, so the slope and the k are somewhat interchangeable. So with that in mind, let's practice something. Okay, we have two pieces of data below, and we're going to say right off the bat that it's a first order rate law. And over here we have the graph of the natural log of these concentrations over time. And what they're asking is to determine the rate constant for the rate of decomposition of hydrogen peroxide using this data. Okay, so remember, to do that, we can set it up by saying that the slope is equal to the change in y over the change in x, right? Change in y over change in x. And as such, we can say that because the slope and the K are related in this way, that the change in the natural log of hydrogen peroxide over the change in time should give us the answer we're looking for, okay? So again, slope and K, negative K equals slope. Slope is a change in in Y over change of X. K is going to be the change in the natural log of the concentration over the change in time, okay? So really all you have to do is pick a couple data points from these trials as your change, going from one trial to another, subtracting them, and then taking the time, the respective time, subtracting those, and seeing what you come up with, okay? Okay, so we can say that because negative K equals slope, slope, we know, is the relationship of how concentration changes over how time changes. And because we have to use the natural log of that concentration to get a straight line, it's going to be the change in some natural log of concentration over time, right? Because let's go back to that slide. Right, the slope of this line is, the slope of this line is based on these data points here, right? And these data points reflect how the natural log of our concentration of reactant changes, or deltas, over time, right? How time changes. So we can set the slope equal to the difference of these changes. So we get this equation here. Now, to do that, we just pick a couple different concentrations on that data table. So we could pick the let's say negative 1.386, which is our natural log concentration at 6 hours, and 12 hours. And then we can subtract it, because we're getting our delta, right? Our delta, subtract it from the 0.693, which is our 6 hour, right? And then take that over delta time. So we said 12 hours minus 6 hours. And so with that, we get negative 0.693 over 6 hours. Okay. And that's going to be equal to a negative 1.55 times 10 to the negative 1 per hour. That's slope, right? So remember, the slope is equal to negative K. So if this is negative, if we just want to repackage this in terms of K, we just get rid of that negative sign. We switch it and say that K is equal to a positive 1.55 times 10 to the negative 1. Okay. So that's first order reaction. Same thing really applies to second order reactions. We integrate them slightly differently because remember, with a second order, it's going to be, it's going to have this exponent of 2 here, right? So that's going to change, the equation a little bit, the relationship of these different components. But it's going to kind of give us, again, a straight line and going to be relative to the slope. All right. So we're just focusing on A, we're just looking at A right here and how it goes to some product, whether that's a decomposition of A or changing to a new molecule. We say that the rate is proportional to the square of the concentration, right? The square, because second order reactions have an exponent of 2. And since, again, we know that rate is equal to the negative change in concentration of reactant over the change in time, we can say that this is equal to now K over the concentration of A squared. So with first order, this was gone, right? But now we put this, because it's a 1 essentially. Okay, so it's going to change things just a little bit. If we then integrate that derived equation, right, this one right here, our integrated rate law now becomes down here at the bottom, okay? A 1 over A equals KT plus a 1 over the initial concentration of A, right? That is our integrated rate law. So you see it's changed a little bit from the integrated rate law of first order reactions. But now that we have this, we do the same thing to answer questions, right? To figure things out, we just plug in variables and solve accordingly. And let's try that. Okay. So here we have butadiene, C4H6. It reacts with itself to get C8H12. Here's the reaction, right? It just doubles these things. It gives us the rate constant, 5.76 times 10 to the negative 2. And it says the initial concentration is 0.2. What is the concentration after 10 minutes? So we're not solving for T this time. We have T, we have A0, and we have the rate constant. So really, all we have to do is plug in things accordingly and solve for A, right? So we are solving for this right here. So you got to do a little bit of algebra to get A by itself. And then just pop in the values and let's see what you get, okay? All right, here is our equation, our integrated rate law for second order reactions. And let's just start plugging in some of the data that we're given. What are we given? We're given K. It says the K is, so 1 over A is equal to the K being 5.76 times 10 to the negative 2, and then the units are liters per mole. Or we could just like that as, oh, it's liters per mole per minute, right? And then, okay, that's okay. Time, they said, was 10 minutes. And then that's going to be all, that's going to be, sorry, ran out of room here, but you see that? It's kind of fuzzy over there, isn't it? And then that's times 1 over the initial concentration, which was 0.200. Okay. So if we take 5.76 times 10 to the negative 2 times 10 divided by 0.2, we should get, change color, 1 over A concentration equals 5.58 liters per mole. Sorry, that's a bad 8. Okay. Why? Because our minutes cancel, right? And let's see, what else? We end up with, now we got to change this, right? Because it's 1 over A. So we take the reciprocal. So to get A, we just take take the reciprocal of that. So we take the reciprocal of this. So 1 divided by 5.58. And that is 1.79 times 10 to the negative 1 moles per liter. Okay, or M. That's how we do second order. Going backward. Yeah. Okay. Going the wrong direction. Okay. So that's what we just did. Here we are. Now, notice, just like with first order reactions, the layout of this integrated rate law is similar to the layout for slope. And so the relationship is similar, only instead of slope being equal to a negative k, slope is equal to k, right? Because we plot it as an inverse, because remember, it's not the concentration of A, it's 1 over the concentration of A, right? So that means it's going to be the inverse of the concentration of the reactant as a function of time. Again, we get a straight line, and the slope of that line is equal to K. The y-intercept in this case is 1 over A, or the 1 over the initial concentration of our reactant that we're looking at, okay? So let's say we have these data and we want to know if it's first or second order reaction, okay? Again, we have butadiene here, so keeping it consistent, and they give us these 2 data tables. How could we figure out if this was first order or second order? Well, we would just plot these here, okay? Because the natural log of this concentration of butadiene, that is data for first order, right? Whereas 1 over the concentration of butadiene, that is the relationship for a second order, okay? So what you can do is pause it here. You don't have to do any Excel stuff. We're going to be doing that for the ICA with this. Just write it out roughly. You can do your y-axis as this concentration, and then your x-axis as time, and then do the same for the natural log, and see which one looks like a straight line. Okay, so I plotted these two out just roughly, so it's not pretty or anything. And this is actually looks like it might be a little hard to see, but this one is looking at second order, so 1 over the concentration of butadiene, and this graph is looking at to see if it's a first order, so the natural log of butadiene. And I just did it in increments of 100, 100, 200, 300, 400, 500, and then for time, 2,000, 4,000, 6,000. For natural log, it's -4, -5, -6, 2,000, 4,000, 6,000. And hopefully what you can see is that this, if you drew a best fit trend line here, that looks pretty straight for me and for just eyeing this up. And if you look at the slope here, pretty not straight, okay? So then what we can do is we can determine that this must be a second order reaction, right? Because it has to be a straight line. Right? Okay. And that brings us to our last, but not, well, I guess last and least, zero order reactions, okay? So in this case, the rate is proportional to the constant, right? Because this essentially has no effect on the rate, right? So we're saying that rate is just equal to K in this case. So if we have our not natural log, not 1 over, it's just equal to K. Or I'm sorry, not K times the concentration of A to the first or to the second. In this case, A to the 0, it just gets rid of it. It becomes 1, right? And so now we have this relationship, this negative change in concentration of our reactant over the change in constant is equal to K. Integrating that, we get the concentration of A, that should be subscript T, not times T. Let's do something here, just clarification. Let's get rid of that, make it down here. So the concentration of A at any point is equal to negative KT plus the initial concentration here, okay? Now, just like the other two, this equation is similar to y equals mx plus b, okay? And so again, the slope is equal to a negative k, all right? So when we're plotting the concentration of a reactant over time, we get, again, a straight line, and the slope is equal to negative k, like first order reactions. The difference is that the intercept is now a to the 0, right? So, you know, same kind of thing. We could do problems, but this is the summary of first, second, and 0 order reactions, and what their y-intercepts are, whether it's natural log or 1 over the natural log of the initial concentration, 1 over the log of concentration of the initial concentration, and then just the initial concentration, okay, for 0 order. And here's a table that summarizes all of these things. So if we are looking at zero order, it gives you the relationship between rate and the constant. Again, it's a to the zero, so it just goes away. First order, it's a to the first, and second order rate is equal to a squared. It gives you units here, and then integrated rate laws here that we went over in this lecture, and then how we plot to get that straight line. Concentration of A versus time, the log of the concentration versus time for first order, and 1 over the concentration versus time for second order. The relationship between K and slope, K is equal to a negative slope. First order K is also equal to a negative slope, or vice versa, slope is equal to a negative K. And in the second order, K is equal to slope. The half-life is what we will get into next time. So with that, we'll call it a wrap, and we'll talk about half-life and maybe some collision theory next time. All right. Take care.